Hey class, Mr. Moyedin here with a video for homework to talk about rotations, symmetry, and congruence. The last several days we've been working in the Cartesian plane, dealing with coordinates, but today we're going to look at these concepts in the Euclidean classical blank plane. Let's take a look. So there are two major kinds of symmetries we'll be talking about, and they are reflectional and rotational symmetry. And sometimes they can kind of overlap depending on how you look at things, but for the most part they're two different kinds of symmetries. And the reason they differ is because the symmetry could occur either along a line or across a line, and that would be a reflectional symmetry. That's the kind of classical butterfly click case. So you could have, it's not a very good drawing of a butterfly wing. I don't know why it's blue either. Let me improve that a bit. So let's say you had a nice butterfly, and then the other wing over here. Of course, the two wings are identical, so hence the idea of symmetry along the line of its body. That's the classical case that most people are familiar with. Of course, this heart shape would have reflectional symmetry across that line. Notice that the Z does not. The two sides are not the same. And the recycling symbol also does not, because again, the two sides are not identical. So there's no reflectional symmetry there. Rotational symmetry occurs around a point. So the point of rotation is important here, as well as the degree measure around which it turns. A phrase we hear a lot is to carry a shape onto itself, or to carry onto itself. So what that basically means is, how can you move a shape around so that you cannot tell that it's been moved? So all of its points correspond directly to points that are already in the figure. For example, if I were to flip or reflect this heart across the green line, you would not be able to tell that I've done so, because the left and the right are symmetrical. Contrast that here. If I flipped the Z across that line, you would be able to tell that I flipped it because it would look backwards. So it does not have a way to reflect, to carry onto itself. And likewise with the recycling symbol. However, there are rotations I can do to both the Z and the recycling symbol to carry it onto itself. So watch for a moment as I rotate the Z, not a full 360, but simply part of the way to carry it onto itself. Now, unfortunately, the software I use is going to make the shape bigger, so ignore the dilation, because remember, rotations are a rigid motion, so ignore the fact it's shrinking and growing a bit. But I did a half turn there, and the Z looks the same. Now, the font I've chosen is not quite perfect either, but you get the idea. And likewise over here, I can rotate this thing around, the recycling symbol. Looks like how we started. Looks like how we started. And looks like how we started. So different types of rotational symmetry in terms of the amount of positions it can be rotated onto itself. So when you see objects with a reflectional or a rotational kind of symmetry, I want you to be aware that it will ask you, among other things, but the first kind of concept it'll ask you about is to find lines of symmetry. So that would be here in this case. And there aren't other ones in these other figures. And to give the order of a rotational symmetry and the degree measure of such a turn. So what do I mean by order? What I mean by order is the number of positions that a shape looks like itself. So for example, if I did a full 360 to this, of course the Z would look like itself. And likewise for the heart. I can give the heart a full 360, so looks different, looks different, looks different. But if I take it back to 360 degrees, oops, again, ignore the dilation. Back to 360, of course it looks like the way it started. So we say that that shape has an order of 1, because there's only one position that it'll ever look like the original, and that's a full 360. The Z, however, is a little bit different. If I were to rotate it around, like I did earlier, it could look upside down, but the upside down is still the same. And then, of course, a full 360, so we say that that's an order of 2. There are two positions, the 180 turn and the full 360 turn, where it looks exactly like itself. And the recycling symbol here has an order of 3, because I can go the original position and then two other turns will make it look like itself. So that would be an order 3. So the order is the number of positions it can be in where it's indistinguishable from its original position. So let's practice this a bit. Here I've given you three shapes, more traditional geometry shapes rather than the other logos and symbols. So what I want you to do is to draw these shapes and also draw the lines of symmetry that it has, so reflectional symmetry, and if you can, determine the order of its rotational symmetry. And that's a bit harder, but give it a shot. So pause the video, draw them, and see if you can answer the questions for each one. Alright, hopefully you're back. Let me show you a very common thing a lot of people will do. Doesn't mean it's right, doesn't mean it's wrong, but they'll draw this line. And say, hey, that's a line of symmetry for this rectangle. No, it is not. If that were a line of symmetry, let me kind of outline the edges here. If this were a line of symmetry for this rectangle, then I could flip the top part of this down here, and you'll see that these two corners do not match up. So the diagonal is a very commonly misunderstood line of reflection. It's not a line of reflection. A rectangle only has two lines of symmetry. This one and that one. So there are two lines of symmetry. Erase that. The order of its symmetry, well, all objects have at least one because they can just do a full 360, but I can give this thing a 180-degree turn. Let me try to avoid making it shrink or grow too much. I've not turned it all the way around, but the fact is you can't tell. It looks like the way it started. So the original position and this 180-degree turn, and then the only other way I can do it is take it back 360, so that's an order of 2. Okay? Here we have what's called a trapezoid. The line of symmetry, the only one, would be this. So there's only one line of symmetry. The order of its symmetry, also interesting. Let's give it some turns and see what happens. So it looks different, definitely looks different. I can ignore the dilation. Okay, that was a 180. That looks upside down, although, and you can quite easily tell that it's upside down in contrast with the rectangle. And now it's back a full 360, so the only position it can look like itself is the original position, so that's an order of 1. And here we have a pentagon, classical 5-sided regular pentagon. It has many lines of symmetry. Here you'll notice a line of reflection, but frankly, so would it be here, so it would be here, so it would be here, and so it would be here. I didn't draw them very well, but connect a vertex, a point, to its opposite side's base, and that would be 5 lines of symmetry. 5 folding reflections you can make. Now the order is also interesting, because what you'll notice is I can rotate this thing quite a few ways. So if I give it just a slight turn, it looks like how it started. And then another slight turn, once again. Now the dotted line, of course, indicates that I've actually turned it, but the actual shape looks identical to how it started. So this one actually has 5 positions, including the original, that will make it exactly like it was. You may be noticing a bit of a pattern here that sometimes holds. Doesn't always, or maybe it does, we'll see. And this one has another question to it, and that's the degree of rotation. How much is it turning each time? So it'll help to think about this pentagon not so much as a single 5-sided shape, but from this center of rotation right here, imagine you have these 5 triangles emanating from it. And we haven't talked a whole lot about triangle congruence, but hopefully you can just look at it and kind of recognize that these 5 triangles should be identical. Well, we know that the sum total of the rotation that I have just marked, let me mark that again in case it was unclear, is 360 degrees. And we're dividing that 360 degrees up into 1, 2, 3, 4, 5 triangles. So if you think about the turn that I'm doing, I'm carrying this onto that corner, that's one rotation, and then here, and so on. Each of those is going to be equivalent to this turn right here, the central angle, you could say, of each one of those triangles. So the degree of rotation would simply be 360 divided up the 5 ways I could rotate it, and what you'll get is 72 degrees. What that means is I can rotate this thing 72 degrees and it'll look exactly the same as how it started. Alright, so there's some basics there of symmetry, reflectional and rotational. Our last topic today deals with congruence. So how can you tell 2 shapes are identical? And the key word here, we've talked a lot about congruence in the past, but the key word here I want us to focus on is sequences. How can you describe a set of steps? So describe in detail the sequence, the series of steps of, when I say steps, I mean of rigid motions, reflections, translations, and rotations, to map one figure onto the other to check for congruence. So what do I mean by that? Here we have a couple of examples. So I want you to go ahead and draw these, and then we'll take a look at how you can say that one shape is like the other. Okay, so the first shape appears to have done the following. You first translate, let me choose a different color, choose black. You first translate along this vector. We've talked a lot about vectors in class by now. So first translate along f prime, that vector. So imagine for a moment what the shape would look like. It might be this blue shape, this crown-looking shape, but sort of where f maps onto f prime and the other points are kind of crooked. They're not mapping onto each other yet. So that's the first step, is simply to slide the blue shape over to the right along the vector f to f prime. And then what needs to happen is a rotation. So you would then rotate about point f, or f prime, because they're already on top of each other, so that d maps onto d prime. So I wish I could move this particular shape, but it doesn't cooperate quite that way. But imagine for the moment that after the translation you'd have something that looks kind of like this, although I'm not a very good tablet artist. Right, the f's match, but everything else is crooked, and then rotating it so that clicks on so that all the points match up. So a series of steps there, a translation and then a rotation that shows one figure onto the other, and that shows you that these two shapes are congruent because everything matches up. Now this one's a little bit easier. If I translate h onto h prime, everything else is going to translate along the same vector, and what you should notice is that those vectors have the same magnitude. So this one actually only requires a single vector. It's a translation. So translate along the vector, whoops, misspelled along vector h prime. But what you could see is that all the vectors are congruent, so you could say any of them, frankly, and all of them would match up. So you're good in that case. So this would be just a single sequence of a single transformation. We'll have one last example, and that's this one here. This is one of my more favorite examples here, because at first you might think, well, I could just reflect, but then the question is, where do you reflect? Do you reflect along that line, maybe that line, and then how do you find the line of reflection? Well, here you want to see there's a couple things that happen. I would say the first way to start is to translate along this vector. So the intermediate step, so the green triangle would be here. I can draw it better than that. The green triangle would be here, L prime, M prime, K prime. And after the translation, the M's match up, so the blue triangle would kind of be like this. All right? So first, translate along M to M prime. But see, these two lines right here, let me outline them more vividly. These two lines right here don't match up yet, and they're supposed to. So this line and this line. Because if you translate along the vector, this will be kind of like this, right? So we then have to rotate about M so that L maps onto L prime. So we rotate it so that these will match up onto each other. So here's our green triangle, M prime, K prime, L prime. We just had the shape sort of in this fashion, but now after a rotation we now have it lined up like so. So the blue triangle is now here. So K prime, L prime, and M. So now we have this line of reflection. So finally we reflect across L, M. So that would be our line of reflection, and boom, K maps onto K prime. So we know that they are congruent. So translate a slide, rotate, turn it so everything lines up, and then finally a flip so that the two shapes fit exactly onto each other. So this is a longer video, but hopefully it sets the stage for some interesting investigations we will do in class this week. All right, I'll see you in class.